In this video I want to talk about how to solve general quartic equations. I will describe a new method that I discovered some years ago and since then haven't published in any form. In the course of making this video I also found a way to streamline one step which previously relied on traditional methods. This step will also be described in this video. This new method I haven't found described anywhere else, so to the best of my knowledge, this method is original. But please let me know in the comments if you have other information. So, what is a quartic equation? A quartic equation is a polynomial equation of degree 4 in one variable, say x. More concretely, it is of the form lambda x to the fourth plus ax cubed plus bx squared plus cx plus d equals 0. Lambda, a, b, c and d are complex numbers called coefficients of the left-hand side polynomial. Our goal will be to find all complex values for x for which the quartic equation becomes true. But if you don't know what complex numbers are, don't run away. To follow this video all you need to know is that they are a superset of the real numbers with some fancy features. And that's, apart from keeping the presentation general, the main reason why we assume the coefficients to be complex rather than real numbers. It shall remind us that we are working over the complex field. This means, we can use its full arsenal, part of which is the ability of taking square roots of any complex number. So, in the process of solving an equation we won't have to worry whether or not we are taking square roots of negative numbers and things like that. Another feature of the complex numbers that we will need in this video is the algebraic closure. But we'll come across that later. Anyhow, there is absolutely no reason to be afraid of complex numbers. All the examples will be real-valued and complex numbers will only appear marginally for those of you familiar with them. In order for the equation to be quartic, the leading coefficient lambda has to be non-zero. But we can moreover assume it to be 1. For, if it's not, we can divide the equation by lambda and we get a new one with the same solutions. We can call the coefficients of our new equation how we like, let's say a, b, c and d. All this goes to say that lambda can be assumed 1 and therefore be omitted. Such polynomials are called monic. Furthermore, we will assume the constant term d to be non-zero because otherwise x equals 0 is one solution and we can divide by x and get a cubic equation. Then, solving this equation gives us the other solutions. In this video I will not talk about how to solve cubic equations. So I will assume that you know how to do that. Otherwise, you can use solving cubic equations as a black box and look it up later if you are interested. So, d being non-zero implies that we can assume x to be non-zero as well. We humans always think in pictures. That's how we roll. Therefore, I deeply believe that no matter how abstract a mathematical field is, you should always somehow try to find a mental image that reasonably fits and from which you can draw conclusions. That's exactly what the great mathematicians do all the time. In our case of solving quartic equations that's not particularly hard. We can treat the value of the left-hand side polynomial for a given x as the y-ordinate of the point whose other ordinate is x. Thus, we get a graph in the xy plane. With this visualization it's easy to see that the solutions to our equation correspond to the positions on the x-axis where the graph touches or crosses it. These positions are called roots of the polynomial. Because we are only considering monic polynomials, the graph can either have one or two local minima. Bear in mind that when regarding the graph of a polynomial, we are only able to see its real roots. So what the graph tells us in terms of real-valued roots is that there can either be 4 different roots, 4 roots with one repeating, 2 different roots, 1 double root, or no roots at all. And there are a couple of other possibilities not covered by the example. Our observations are perfectly in line with the fundamental theorem of algebra, which states that every single variable polynomial of degree n has exactly n not necessarily distinct complex roots. The complex numbers being a superset of the real numbers, means that some, or even all, of the complex roots might also be real. And that's what we saw. For instance, in the example right now, we see that the graph crosses the x-axis twice, so the polynomial has two distinct real roots and two non-real complex roots. As a consequence, we can write the left-hand side of the equation as a product of linear terms x minus x1 through x minus x4, where the xi are the complex roots of the polynomial. We will need this fact later. To motivate the new method, I will present examples of increasing difficulty and discuss how they can be solved. This will culminate in solving general quartic equations using the new method. Since in the course of solving the examples we will heavily rely on substitutions, let's ensure that we are on the same page and let's briefly talk about what a substitution is. Loosely speaking, a substitution is a replacement of a part of the equation by a term in another variable, say u, such that the rest of the equation can be written as a simple expression in that variable. In the simplest case, we replace x by a term f of u. For example, a popular substitution is x equals u plus h, where h is an appropriate constant. If we replace x by the expression u plus h, we get an equation in u. In this example, we see that after expanding and collecting equal terms we get again a quartic equation, this time in u. The coefficients of our new equation depend on the coefficients of our initial equation and the constant h. For convenience we will call them a prime, b prime, c prime and d prime. But why do we even bother with substitutions? After all, we obtain just another equation. In mathematics, substitutions are always employed to get a nicer form of the equation which is amenable to some special tricks or treatment. Therefore, substitutions are sometimes also called transformations. And our example demonstrates that rather nicely. As said, the coefficients of our equation in u depend on h. For example, a prime is equal to 4h plus a. If we were to choose h as minus a over 4, a prime would become 0 and the cubic term would disappear. This is known as linear Chern-Haus transformation. We can do all sorts of transformations. For instance, we could make the quadratic term disappear by setting h appropriately or enforce some other conditions on the coefficients if they are beneficial. And that's precisely the key idea of my new method. But more on that later. As we have just seen, quartic equations can be visualized by considering their associated graphs in the xy plane. Here we have two equations, the graphs of which we can draw in the same plane by treating the values of u as the x-ordinates. That way, by studying the relationship between these two graphs, we can also visualize transformations, at least simple ones. Returning to our example x equals u plus h, we have a quite vivid relationship. If you think about it, you will realize that the graph of the transformed equation is just a shifted version of the initial graph along the x-axis. The value of h tells us how far the graph is shifted and to which side. You might want to pause the video and convince yourself that this is really so. Now, suppose we have managed to find the roots of the transformed polynomial. Then, in order to obtain the roots of the original polynomial, we only need to unshift them and voila! We got our solutions. In this video, we will also encounter more complicated substitutions which cannot be visualized in such an obvious way. But perhaps you are able to come up with a creative illustration. Yet, the same principles apply, although the unshifting process, so to speak, isn't as trivial. Still, it won't be fundamentally difficult either. So we know what a substitution is. Let's tackle our first equation. As a warm-up, let's consider this one. We see that the equation contains only even degree terms in x. Such equations are called biquadratic equations. Solving biquadratic equations is easy. We can set u equals x squared. Then, x to the fourth becomes u squared and we get the quadratic equation. u squared minus 7u plus 12 equals 0. Using our favorite quadratic formula, and doing some algebra, we get two values for u equals 4 and u equals 3. All we need to do is to express these values in terms of x and we are done. But that's straightforward. Remember, we set u to x squared. This means that x is plus minus the square root of u. Plugging in the values for u gives the solutions. X equals plus minus 2 and x equals plus minus square root of 3, of our initial equation. That was easy, right? But what about this equation? We see that the first and the last coefficient are equal. The same is true for the second and second last coefficient. Therefore, this type of equations is called symmetric. But how can we exploit this symmetric structure? First, we divide the equation by x squared. Remember, we can do this because we have assumed x to be non-zero. Next, we rearrange the equation such that equal coefficient terms are side by side and factor out x plus 1 over x. But what's the point of doing that? Well, we can make a clever substitution. We set x plus 1 over x to u. The clever thing about the substitution is that we can express the rest of the equation by a simple term in u. That is to say, using the binomial theorem, we get u squared equals x squared plus 2 plus 1 over x squared, so that x squared plus 1 over x squared becomes u squared minus 2. We plug that in and get a quadratic equation in u. This we can solve using our favorite quadratic formula. And after some steps, we get the solutions u equals 1 and u equals minus 4. Now, all we have to do is to express these solutions in terms of x. So we solve for x, again using our favorite quadratic formula, and we get this. Finally, we plug in the values for u and we get two complex solutions along with the real solutions minus 2 plus minus square root of 3. Now, if you are unfamiliar with complex numbers, just forget about the complex nonsense. In that case we have only two solutions. Now, you might think, can't we do a slightly more general substitution to solve yet an even larger class of equations? And you are perfectly right. Consider this example. If we factor out 3 from the linear term and write the constant term as a square, we see some kind of almost symmetric structure but no real symmetry. Such instances are therefore called quasi-symmetric. We will come to the exact definition in a moment. Let's start with the same trick as before and divide by x squared. After rearranging the equation such that the x term and the minus 4 over x term are next to each other, and factoring out 3 from these terms, we see that the substitution x minus 4 over x equals u imposes itself. The crucial point is that the equation is of such form that the rest of it can be expressed as a quadratic function in u. Squaring u, we get u squared equals x squared minus 8 plus 4 over x squared. Hence x squared plus minus 4 over x squared can be written as u squared plus 8. So again, we get a quadratic equation in u. This time, the equation is particularly simple because it can be factored into u times u plus 3 equals 0. And we immediately get the solutions 0 and minus 3. Now, as before, we solve for x and plug in the values for u. and finally get plus minus 2, 1 and minus 4 as solutions for x. What we've seen up to now is the traditional method of solving quasi-symmetric equations. Now, I want to show a new idea. Let's take a general quasi-symmetric polynomial x to the fourth plus px cubed plus qx squared plus lambda px plus lambda squared. The aim will be to find quadratic polynomials p and q such that the quasi-symmetric polynomial can be written as a product p of x times q of x. For this purpose, remember that we can write any polynomial as a product of x minus its complex roots. Here, lambda squared is the constant term which we assumed to be non-zero. Because lambda squared is the product of the roots x1 through x4, this can be easily seen by expanding. This means that the roots are also non-zero. If we plug in x1 for x, we get this equation. We multiply it by a lambda squared over x1 to the fourth, and after some simplifications, we get this. If we denote the former left-hand side by f of x1, we see that the latter left-hand side just happens to be f of lambda over x1. This means that x1 being a root of the polynomial implies that also lambda over x1 is a root of the polynomial. In other words, one of the other roots, say x2, must be equal to lambda over x1. So we can replace it. But we can apply exactly the same reasoning to x3 and replace x4 by a lambda over x3. Next, we multiply the first two linear factors and we get a quadratic factor. As x1 plus lambda over x1 is just a constant term, we write it as alpha to get a more compact form. We do the same with the last two linear terms. And get the quadratic factor x squared minus beta x plus lambda. Thus, we have expressed our quasi-symmetric equation as a product of two quadratic polynomials. Now comes the cool part. Our considerations have led to some insights about the quadratic factors. And this turns out to be enough to explicitly determine these factors, which is to say, solve for alpha and beta. To do so, we expand the right-hand side, collect equal terms, and compare the coefficients on both sides. Thus, we get a system of equations in alpha and beta which we can solve rather straightforwardly. First, we solve for beta in the first equation, and plug that into the second. After some rearranging, we get a quadratic equation in alpha. In the expression for alpha, we replace the big square root by d for aesthetic reasons. So we get minus p plus minus d all over 2 for alpha. Plugging this into the first equation, yields a similar expression for beta. We see that we have a choice for alpha. Whichever we take, beta gets the other one. But as alpha and beta appear symmetrically in the above factor decomposition, it doesn't matter which choice we take. Both yield the same decomposition. So we just take one. Finally, we plug in the expressions for alpha and beta in the formula and we have obtained a product formula for the quasi-symmetric equation. Let's briefly talk about the formula. Even if p, q and lambda are real numbers, d can still be non-real. This occurs if the term p squared minus 4q plus 8 lambda under the root happens to be negative, and we can't rule out this possibility. So if you are going for complex solutions, you just continue normally with a complex value d. At this point, it can be concluded that all four solutions will be non-real. If on the other hand you are looking for real valued solutions only, you can stop at this point since there are no ones. In our examples however, d will always be a real number. Now let's use our new formula to solve the previous example. As the equation is quasi-symmetric, by definition we get lambda as the quotient of the linear and the cubic coefficient. So lambda is minus 12 over 3, better known as minus 4. Then, the values for lambda, p and q yield the value of d, which ends up to be 3. With these values we apply the formula to our quasi-symmetric equation, and after some simplifications, we get x squared plus 3x minus 4 times x squared minus 4 equals 0. The advantage of writing the left-hand side as a product is that it allows us to solve the equation right away. Because a product is 0 if, and only if, one of its factors is 0, we get the two quadratic equations x squared plus 3x minus 4 equals 0 and x squared minus 4 equals 0. And solving quadratic equations is no big deal for us by now. Using our favorite method we get the solutions. (1, minus 4 and plus minus 2). As expected, we got the same solutions as before, but without the need of employing substitutions. This comes however at the cost of an additional formula. So, what do you think about this new approach? What about this one? Clearly, it's not biquadratic and neither is it symmetric nor quasi-symmetric. Apparently, it's a general equation. So how can we solve it? Let's try the substitution x equals u plus 1. If we apply it and simplify the resulting equation, we get u to the fourth minus 4u cubed minus 42u squared minus 36u plus 81 equals 0. But what's the point? Let's write 36 as 4 times 9 and 81 as 9 squared. Does that ring a bell? Yes, we've got a quasi-symmetric equation. And we know how to solve that. We invoke our product formula for quasi-symmetric equations. For lambda we have 9. And plugging this into the formula for d, we get d equals 16. Using our formula we write the equation as u squared plus 6u plus 9 times u squared minus 10u plus 9 equals 0. Because a product is 0 if and only if one of its factors is 0, we get the quadratic equations u squared plus 6u plus 9 equals 0 and u squared minus 10u plus 9 equals 0. We solve them using our preferred method. And we get the solutions minus 3 and 5 plus minus 4. To obtain the solutions for x we plug the values for u into our substitution formula. And in the end we get minus 2 and 6 plus minus 4 as solutions for x. Consider this equation. Again, it's not quasi-symmetric nor biquadratic. And I promise, it has no other hidden properties that I'm aware of, other than the solutions not being too complicated radical expressions. So it's fair to say that we have a general equation in front of us. But how are we supposed to solve it? Let's try the substitution x equals u minus 2. After applying it and simplifying, we get u to the fourth minus 2u cubed minus 10u squared minus 14u plus 49 equals 0. We write 14 as 2 times 7 and 49 as 7 squared. And can you see it? Yes, once again we've obtained a quasi-symmetric equation. Hence, we can again use our product formula for quasi-symmetric equations to solve it. Lambda is 7 and plugging this into the formula for D. We eventually get 10 for D. So, the equation can be written as u squared minus 6u plus 7 times u squared plus 4u plus 7 equals 0. This yields the two quadratic equations u squared minus 6u plus 7 equals 0 and u squared plus 4u plus 7 equals 0. Solving them using our favorite method, we get the solutions. Three plus minus square root of 2 for u, along with two complex solutions. Plugging these values for u into our substitution formula, for x we get the real valued solutions 1 plus minus square root of 2, together with the complex solutions minus 4 plus minus I times square root of 3. If you're only interested in real solutions, then just forget about the complex stuff. In that case, the equation has only the two solutions 1 plus minus square root of 2. So what's going on? Magic? Those of you familiar with Galois theory probably already suspect that behind the magic hides a cubic equation. And indeed, any quartic equation can be turned into a quasi-symmetric one by means of a linear substitution x equals u plus h. To find an appropriate value for h, recall that in order the transformed equation to be quasi-symmetric, the cubic coefficient has to be of the form p. The linear coefficient of the form lambda p, and the absolute term of the form lambda squared. This gives rise to an equation for h which obviously must hold if the transformed equation is supposed to be quasi-symmetric. The good thing about the equation is that it is also sufficient, meaning that its solutions indeed yield a quasi-symmetric equation. You can pause the video and convince yourself that this is really the case. On the minus side, we have a real monster equation in front of us which is really messy, and I mean really messy. There seems no hope of solving it. But by a series of simplifications most of the mess mysteriously disappears. Just watch and relax. Here, we have a difference of squares, which we can write as a product. Weirdly enough, we have arrived to a cubic equation which can't be reduced further. So, we bring everything to the left-hand side and factor out the powers of h. In the end, we have obtained a relatively simple cubic equation for h which can be solved. Any value satisfying the cubic equation yields a quasi-symmetric equation. And if the coefficients a, b, c and d are all real, then there is also a real value for h satisfying the equation. Hence, if you're only interested in real-valued solutions, you don't have to make an excursion into the complex numbers to get them. To wrap this video up, let's do a complete solve of a general quartic equation using our new method. Consider this example. The first step is to transform the equation into a quasi-symmetric one by means of the substitution x equals u plus h. To find a value for h, we invoke our cubic formula for h. Plug in the values of the coefficients. And, after some simplifications, we get 25h cubed minus 625h squared plus 1075h minus 475 equals 0. Luckily, we can divide by 25. And we get h cubed minus 25h squared plus 43h minus 19 equals 0. One solution to this equation is h equals 1. So we obtain the substitution x equals u plus 1. For h we could have taken any value satisfying our equation, but it's obviously easier to apply the substitution x equals u plus 1 than the substitution x equals u plus 12 plus minus 5 times square root of 5, which corresponds to the other two solutions. Again, I will not describe how to solve cubic equations. You can look it up elsewhere if you're interested, or wait for a hopefully forthcoming video. Once we know how our transformation looks like, we apply it. And after expanding and simplifying, we get the quasi-symmetric equation u to the fourth plus u cubed minus 14u squared minus 4u plus 16 equals 0. In the second step we apply our formula for quasi-symmetric equations. As in one of the previous examples, lambda is the quotient of the linear and the cubic coefficient. This is simply due to the structure of quasi-symmetric equations. Thus, lambda is minus 4. And plugging this into the formula for d, we get d equals 5. With these values we obtain a product form of the quartic equation in U. Because in order the left-hand side to be 0, one of the factors has to be 0, we get the quadratic equations, u squared plus 3u minus 4 equals 0, and u squared minus 2u minus 4 equals 0. Upon solving them using our method of choice, we get the solutions. (1, minus 4 and 1 plus minus square root of 5 for u. Finally, to get the solutions for x we plug the values for u into our substitution formula, and in the end we obtain 2, minus 3 and 2 plus minus square root of 5 as solutions for x. And this completes the presentation of the new method. So what do you think about the new method? If you already know other ones, for example the Ferrari method, which do you like more and why? Also, what do you think about my first video? What could be done better? Please tell me in the comments below. Thanks for watching, and bye for now.